Hello everyone, welcome to DKodeTree. Today we are going to solve LeetCode 700 search in a binary search tree. This is a very fundamental topic in DSA, and even though I didn't really use BSTs during my time at Google, but they are super important for interviews and for building strong DSA foundations. And believe it or not, many modern data structures actually use tree-based designs similar to BSTs under the hood to organize and retrieve data efficiently. So before we jump into the solution, let's quickly understand what a BST actually is. A BST or a binary search tree is a special kind of binary tree that follows this simple rule. Given a root node, all the nodes in the left subtree are less than the value of the root and all the nodes in the right subtree are greater than the value of root. And this property holds true for every node in the binary search tree. In simple terms, you can remember the BST property as left subtree less than root less than right subtree. If any binary tree follows this rule for every node and has no duplicate values, we call it a strict BST. And usually when we say BST, we are simply referring to a strict BST unless specified otherwise. In this problem, we are given the root of such a binary search tree and we need to search for a target node value in it. If the value is present, we return the corresponding node and otherwise we return null. And here returning a node means returning the entire subtree rooted at that node. I will show you both the recursive and iterative solutions to this problem. The first idea that might come to anyone's mind is to do a simple binary tree traversal using any traversal technique like pre-order, in-order, post-order, or level order traversal. All of these traversals will eventually give a valid result since every node is visited in this process. So while traversing, we can easily check if our target node is present or not in the tree. However, since in each of these traversals, we need to visit every node in the tree, so the time complexity of this approach becomes O of n, where n is the number of nodes. Now the question is, since the input is a BST and not a simple binary tree, can we do any better by leveraging its BST property? And it turns out yes, we can. Thanks to this BST property, we can complete the search for our target node even without needing to visit every node in the tree. So suppose we are given a BST with root node 5 as input and we have to find the target 4 in the BST. So we'll start our search from the root node and we'll compare it against the target, that is 4. And since 4 is actually less than 5, so it is very clear that we need to search for this target node somewhere the values less than 5 can be found. And from this equation, we know that the left subtree contains the values that are less than the root. So the target, if present, it must be in the left subtree. Suppose this pointer is tracking the current node being compared. So after this first comparison, we will move it to the left side of the node, that is 3. Next, we compare the target 4 with our current value 3. And now, as the target 4 is actually greater than 3, so the target must be somewhere in the right subtree of the node. Because each node follows this BST rule, where the values greater than the current node will be present in the right subtree of that node. So after this comparison, we will simply move our current pointer to the right child of the current element. Now again we compare our target element with the current node and this time they match. So we'll simply return the node with the value 4 as result. Note that for the leaf nodes, both the left and right child are null and we are actually returning the subtree rooted at 4 as the result. And suppose if the target was actually not present in our tree, then after doing all the comparisons, we would definitely reach a null node and we could simply identify that the target is not present and return null as the result. As you can see, in this approach, we only made 3 comparisons here. But in the previous traversal approach, we would have made n comparisons. So in general, while searching in a binary search tree, we only need to compare the target value with one node at each level if done efficiently. And that's what makes this approach so powerful. It drastically reduces the number of comparisons as compared to the simple traversal approaches. And in our example, since the tree has only 3 levels, so we just made at most 3 comparisons in total. And that means the time complexity of this approach is only O of h, where h is the height of the binary search tree. But remember that for a balanced BST like this one, the height h is generally about O of log n. But for a skewed BST like this one, the height can go up to O of n in the worst case. This means the time complexity of this approach depends on whether the BST is balanced or not. Still, in most practical cases, this method is much more efficient than doing a simple traversal. And the space complexity of this approach actually depends on how we implement it. The recursive approach takes O of h extra space because of the recursion stack which grows with the height of the tree. But in the iterative approach, we don't use any extra space. So it works in just O of 1 memory. So now let's code this up. So first I will quickly implement the recursive solution and then I will show you the iterative solution as well. So for any recursive solution, the most important part is the base case. And in most tree related problems, the simplest base case is to check whether the root exists or not, which we can easily do using the condition if not root. So if the root is none, that means we have reached the end of a branch, so we just return none. Obviously, other problems might need additional base cases depending on their logic. Next, we check if the target value is actually less than the root node's value. And if it is so, then we will move our search to the left subtree. So we can simply return self.searchBST of root.left and we'll pass in the target value as well. So this will actually do a recursive search on the left subtree. Otherwise, if the target value is actually greater than the root.value, in that case, we will move our search to the right subtree. So we will return self.searchBST of root.right and we'll pass in the same target val. And finally, if the value is neither less or greater than the root.value, that means it must be equal to the value at the root. So we can simply return the root as our result. So that's all we need to do in the recursive implementation. Let's run this quickly. We can see that this is accepted and let's move quickly to the iterative solution. So for the iterative solution, we will simply take a pointer called current and we will point it to the root node. Now we will run a while loop which will run till current is valid. That is, current does not become null. In that case, once we are inside the loop, we will simply check if the target value is actually less than the current dot value. And if it is, then we will move our current pointer to the left child. So current is equal to current dot left. Otherwise, if the target value is actually greater than the current dot value, in that case, we will move our current pointer to the right child. And if both the values are equal, which will come in the else condition, we will simply return current as our result. So now once the while loop is over, when the current reaches a null node, that implies we haven't found a matching target inside the tree. So we can simply return none as our result. So this is all we have to do for the iterative solution. We'll simply run it. And we can see that this is also accepted. You can find both the solutions on my website DKodeTree.com. Feel free to check it out. If you found this helpful, hit the like button and subscribe to the channel for more such videos. Till then, keep preparing and I will see you in the next video.